Hey guys, this is Angel, and in this video we're going to expand off of the Newton's second law video that we witnessed in this playlist. And we're going to begin by looking at a pulley system problem. Now this is pretty straightforward, and we're going to look at a sign and equilibrium problem next that is going to be a little more complicated. But this scenario reads, a crate of 15 kilograms is attached to a massless rope that is part of a frictionless pulley system. What is the force required to raise the crate with a constant velocity? So we discussed in Newton's second law video that if there is a net force, so if this force value is equal to any number other than 0, then there is an acceleration. If that number is equal to 0, the net force is equal to 0, this means that the object is either at rest or at a constant velocity. So what this is asking, what is the force required to raise the crate with a constant velocity? What we need to know is what forces are acting on this crate and how can we oppose them so that we get a net force of 0. So if we were to draw a free body diagram, we would have the force of gravity coming down and we would have 150 newtons coming down because it's a 15 kilogram crate. So what force do we need to oppose that in the opposite direction and inhibit an acceleration? We would need 150 newtons upward in this rope, the tension in the rope. So the answer to the first question is 150 newtons. We want to get that net force here equal to 0, so that way our acceleration is equal to 0. All right, so now second problem. What is the tension experienced in the rope if a 250 Newton force is applied to the opposite end? So the reason I included this question is because I ran into something very similar in MPrep. It's a very useful little email list that will give you a MCAT question every day to help you practice and prepare for the MCAT. Definitely recommend it. It's MPrep. In one of the questions, it gave me a very similar scenario: crate with a rope, and then somebody pulls on that rope with a certain amount of force, and it asks what is the force experienced in the rope. Now, my intuition told me to find the difference between the force of gravity and the force that was being provided. That was incorrect. My intuition lied to me. What you want to think of the rope as is a method of transporting force. So if we were to put 250 newtons here, if we were to pull that down, then that rope is simply serving as a manner of transporting force. And so our free body diagram would still have now this would be in the air. Our free body diagram would still have the negative 150 newtons as force of gravity, but now upward we would have the tension of the rope with the 250 newtons, because that rope is simply transporting the force provided on one end to the other end. And that's also where it becomes important that the pulley is frictionless, because no force is lost at the pulley. So the tension experienced in the rope of 250 newtons applied to the opposite end is 250 newtons. That force is simply transported by the rope. All right, so now the third question, what is the magnitude of the acceleration experienced by the crate? I'm actually going to bring back that free body diagram. So as we discussed just earlier, I'm going to continue discussing, is what is our net force? How does that relate to acceleration? Well, the forces that we have acting on here are the force tension force minus the force of gravity. That's going to give us our net force in the vertical direction. And then our mass is 15 kilograms. And our acceleration is what we're looking for. What is the magnitude of the acceleration of the crate? So just mental math, 250 newtons from the tension force minus the 150 newtons from the force of gravity. And I should really put that as plus. When we do that pretty straightforward math, that we get that 100 newtons is the net force now acting upon the crate, the 15 kilogram crate. And so we would do 100 newtons divided by 15 to get our acceleration. And in doing that, we would get that the acceleration is equal to 6.67 meters per second squared approximately. So for the second problem, we're going to go ahead and do a little bit more of a complicated situation where we've got a 300 Newton sign in equilibrium being held up by two wires that are equivalent. They're at the same angle, and those two wires are holding up this 300 Newton force, this 300 Newton sign in equilibrium, so that it is not experiencing any acceleration in the vertical or horizontal direction meaning that our net force is going to be equal to 0 in both directions. So the first thing that it wants us to do is draw the free body diagram. And so in doing so, we've got the 300 newtons down, and it gives us the weight instead of the mass of the sign, so that'll make it a little easier. We don't have to calculate the weight. We can just go ahead and directly put it in. And then we've got 35 degrees above the axis for those two wires right there. So I'm going to just go ahead and draw the axis for us so it'll make it a little easier to visualize. And so now what we want to know is how much tension is experienced in each wire holding up the 300 Newton sign in equilibrium. So each wire, how much is this force tension? So we'll call this force tension 1, and we'll call this force tension 2, and then down here we have the force of gravity. So we know that each wire has some components of force that are not demonstrated here in the free body diagram, but they do exist. And those are the vertical and the horizontal components, like so. Those horizontal and vertical components are what is helping keep the sign in equilibrium. These horizontal components that we'll call Fx, negative Fx, and positive Fx are stopping the sign from accelerating in either the left or the right direction. And then these vertical components we'll call Fy, Fy2, Fy1. Those vertical components are adding up to oppose these negative 300 newtons here. So they're adding up to 300 newtons in the positive upward direction. So we don't necessarily need to do the math to determine what each one of those vertical components is. We can assume that because they're the same, each one must be equal to 150 newtons. So Fy1 is equal and Fy2 are both equal to 150 newtons, and the addition of those 150 newtons oppose the negative 300 newtons of gravity, and so that's what is making the net force equal 0 in the vertical direction, and then these opposing forces in the horizontal direction are what is causing the net force to equal 0 in the horizontal direction. So now we have another part of the triangle in the free body diagram, and that newly found force is going to allow us to determine the tension force in each of the ropes. So we just found that these forces here are both equal to 150 newtons, and this is also equal to 150 newtons. And we've got an angle of 35 degrees, but what we're looking for in the problem is this tension force here. Now they're the same on both sides, so we can solve for just one side and get both of them. And this should be 35. And so we can do our trigonometric functions to determine the force tension in the rope. So what we would want to do is we'd do the sine of 35 degrees is equal to 150 newtons over the tension force. And when we solve for that tension force, we get that the tension force is equal to approximately 261.5 newtons. And so that gives us 261.5 newtons in each of these tension forces from the wire.